lets us create a local environment with a variable. So the example we saw at the end of class last time was we defined a function. We defined it named blah. Blah is a lambda expression that takes in a single parameter. And then inside that, we create a let, which creates a local environment where we've bound two variables. C is equal to 5, D is equal to 9. And then we do some math by adding A and C together, A being the variable passed into the lambda, C being a local variable defined with the let, and we multiply that by D. So we're using local and less local variables there. So a let allows us to pull that off. That make sense? Creates a local environment for defining variables with corresponding values within a lambda expression. So to kind of give you a comparison of how we would have done this previously, I could have said define E to be 5, define F to be 9, and then inside of, well, here, I'll just define the second thing. Define blah 2 to be a lambda that takes in an A, and we're going to multiply plus A E and F. And then we'll call blah 2 on 10. So here's blah 2. Blah 2 is going to take in a 10 as a parameter. What are we going to do? We're going to take the 10, we're going to add to it whatever E is. E is a global variable defined here, outside of that. So that'll be a 15. Then we'll multiply the 15 by 9, which gives us what? 135? Oh, I already had a variable up there named E. So let's call this guy Q. Make sense? So this would be an example of creating two global variables that we can then access within a method, as opposed to having a method self-containing two local variables. That make sense? Okay. Now, let's look at some of the limitations of a let. Let's see, that was originally 9, right? So let's add 4 to it just so our final answer will be the same. So now I'm going to use a let, and I'm going to define two local variables. The first one is going to be C, is 5. The second one is going to be D, and I want D to be equal to C plus 4. Okay? And we run into a problem where C is not defined. The let expression does not allow us to define variables in terms of other variables. Mr. Quiz?
Oh, really?
Yeah? Don't you see the papers laying right there? So where is Dane today? Dane's caught in an infinite parenthesis loop.
He's writing parentheses on the wall. He's going.
All right, so we see that we have a problem, a limitation of the let that says we cannot define another variable in terms of a variable. So we define C right here, and from our perspective, C should already go ahead.
Is that if it's just within the let statement?
Correct.
If it's previously defined?
We could do it in terms of A.
Okay.
Actually, that's weird. Oh, I'm still doing blah 2 here. That's why. There we go. Yeah, you could do it. Punchline here is that when we're defining D here, the environment that was created with the C does not yet exist. We're in the process of creating an environment. Does that make sense? So we can't have D, we can't have the process of defining D refer back to C because of how it works. Okay? So we have a second version of let, a more powerful version of let called let star. And let star will allow us to define a variable in terms of another variable. So notice I just added the asterisk there to the end of let, no spaces. So another function called let star. And let star allows us to implement something in such a way that we can define another variable in terms of a variable that was defined before it. So, as an example, I'm going to say C is equal to D and D is equal to 9. Okay? It is linear. It requires that certain things happen before other things. So I cannot use D before it's been defined. This kind of goes back, if we're going to relate this to a programming language concept, it's kind of like early versions of C and C++ compilers that were one-pass compilers, where you had to prototype functions before you used the functions. If you intended to define the function later on, you couldn't use a variable until after you'd had defined it, even if it was later on in the program. So let star is like a let, except we can define variables in terms of variables already defined within the let. That make sense? No. This slide? Okay,
Why
there.
does the normal version of the let even exist?
There, it's up. Well, let's say you're writing a program. I mean, it's a fair enough statement. You could say the same thing as, why are there so many versions like EQ, EQV, and equal? You know what I'm saying? Where you can just always use equal, and it will work. Equal is like going to the hospital and getting the MRI, which looks at everything, as opposed to going to the hospital and they take like just a quick 5-minute X-ray and have some dude come and look at the blurry picture and decide if something's broken. You know, if everybody took the MRI, you'd have a whole lot more information much earlier. Why don't they give an MRI to just anybody? It's expensive. Yeah, MRIs they're not time. I would say how many of you have had an MRI before? One and a quarter people?
Takes time to schedule it.
Oh, the only times I've ever had an MRI is when they don't know what's wrong with me and they rush me down to the MRI.
Okay.
What are you talking about?
Oh, I've had ultrasounds.
Oh, well, yeah, MRI is different than an ultrasound. But in any case, the punch. I mean, an MRI. Let's say. That's probably true. Scheduling anything with a hospital takes time, right? So if it's an emergency type thing, then they somehow find the 3 minutes it takes to send you into the MRI. But if you get an MRI done, it's just a machine. You go into the room, you lay down on this table, they push you into it. I have to actually go to the special ones that can house fat people. It's true story.
Those would be like,
And all the new ones work that way. The new ones look like a big donut. You're not like inside of an enclosure. But the old ones, not that old, but older ones are like almost like a tube slide, and you go into it and it makes all these noises and stuff. I don't quite fit, and it's kind of like they can get me in there, but there's friction. And I don't think like your gut and stuff is supposed to be pushing up against the walls. They want some clearance. Is the point? But in any case, the whole MRI takes 3 minutes or something like that. It just goes through a whole thing, just basically scans your whole body. It can do whatever it wants. But the reason they don't do it for just everything is because it's really, really, really expensive. So same thing would be true here. Now, to go back to Tina's question, why don't we always just use a let star? As programmers, maybe we would. As programmers, maybe we'd say, look, we don't care about performance. But right off the bat, if we're using a functional language, which is almost always an interpreted language, we're already at a disadvantage when it comes to performance. Computers today are pretty quick. Would we actually notice? Probably not. So it's not a great answer, but it's a reason. So a reason that you wouldn't always use a let star, or the reason that a let even exists, is so if you don't need to create a local environment that's in terms of your other variables in it, a let is good enough, and since that's your lowest common denominator, that would be the one that's easiest to implement, and therefore would be the one that's highest performance. It would fall very similar to why don't we always, if you're not storing a number bigger than 128 in Java, why don't you just store it inside of a byte? Yet we all use an int, right? You gonna cry?
no,
Do it.
no.
Do it. That'd be really funny. What'd you do?
Funny boned it. It's not so funny.
Okay, so does that make sense? So let star allows us to do things in terms of other elements in there. I need to check something here real quick. What was I talking about?
Are you going to let us go, or are you not?
Okay. So, now let's say that we want D. Actually, here, we're going to do this. We're going to write blah more bestest. In fact, we're going to start it with a let. And we're going to say that we have something called fact. And fact is a lambda that takes in a, actually let's start with something simpler. Let's say add 1. And add 1 is going to be a lambda that takes in a single parameter and takes whatever that parameter is and adds 1 to it. That make sense? And we'll just leave it at that. Now we're going to go and say add 1 of A. So I can define functions in terms of a let. Remember, functions are first-class objects inside of Scheme, which is why we define variables like Q and F in the exact same way that we define a function. The difference is the value of a function is a lambda. The value of Q here is just a literal 5. Does that make sense? So nothing keeps us from creating a variable inside of a let whose value is a function. That make sense? Okay. So now let's go back to what I was doing before. You probably weren't paying attention, so you probably missed it. I originally was going to call this guy fact for factorial. Factorial would take an x as a parameter, single value as a parameter, and it would do what? Remember the factorial, like factorial 4 is 4 times 3 times 2 times 1. It would ask the question. It would say, if x, so if x is equal to 1, then return 1. Otherwise, multiply x times the factorial of minus x1. And then we'll call fact on A. So this is a function called fact that takes a single parameter. If that parameter is currently equal to 1, just return 1. Otherwise, multiply whatever it currently is times calling fact again recursively on 1 minus the current value. That makes sense? So that's the recursive version of factorial. And then I'm going to call it on blob. And we'll get the factorial of 4 here, which should be 24. Yet we have an issue. Fact, this function is not defined. So I'm trying to use something before it's defined. Now, let star allows us to define other variables in terms of a variable that we've already defined. Now I'm trying to use a variable in terms of itself. Let star doesn't cut it. So we have a third version called let rec. And let rec allows us to define a variable in terms of itself. That makes sense? So let star, like let, except we can define variables in terms of variables already defined within the let. Let rec, like let and let star, except we can define variables in terms of themselves, i.e. supports recursion. That makes sense? So now we need to go back. So, well, first of all, do we understand the whole let star, let rec? We understand that dealie. So if I asked you again next class, gave you a quiz, asked the same questions today, everybody would get it right?
Slight chance.
So it's a slight chance that everybody would get it right. Okay. So now that we understand how to create local environments, do you think that we probably want to go ahead and add to the Simon language the ability to create a let expression? Except in Simon, we might not call it a let. Simon, we have a, actually, do we have lambdas? Oh, we do. So we might as well do a let. Since Simon is kind of scheme-like. We're implementing a simplified version of scheme in scheme. And then writing a parser that converts it to Bazel code. And then applying Bazel code. It's the ultimate goal. Say what? Okay, so this is a literal expression. Here's a var expression. Here is a this is our var def expression. var-def expressions don't make sense in our language. We talked about this last time, right? That's the whole reason we introduced lets. Because we're dealing with a functional language, we never have the opportunity to actually define a variable. We can't inline define a variable. A let allows us to inline define a variable. So we're going to go ahead and replace this guy with a let. That is somebody whose car is the word let. And we're going to start off with a simple case, just the let. Okay? And a let is going to be what? It's going to be a var-def expression. That's what we're creating. And a let has what? So if we go down here and look at our example, here's an example of a, well, let me give you a simplified example of a let here. This is actually an interesting question. Why was the result of that 12? I define blah here. Somebody who usually doesn't answer a question. This is your Java knowledge should follow through with this. So this is what blah is right here. And I'm passing in 4 as my example. So 4 comes in for A. The result here was 12.
Oh, because you redefined A as 5.
I have every variable boils down to its most local definition. The most local definition of A here is this definition of A, not this one. Does that make sense? Java works the exact same way. All right, so here's an example of a let. And here, let me, just so there's no confusion, we'll write it like that. But here is the actual let expression right there. What are the parts of a let? What are all the, if you had to define the individual pieces that make up a let, what are the pieces? I'll get us started. The first piece is the word let. What's the next piece? Variable environment. That is a list containing 2 lists. Okay, a list containing, in practicality, 1 or more 2 lists. We wouldn't be using a let unless we were defining at least 1 variable, right? Otherwise, we're just being stupid. In fact, I actually wonder, will it allow us to do it? I'm thinking this should give us an error. No, it doesn't. That's just... So that means that the definition of a let says that the variable environment can be the empty environment, where you've literally wasted everybody's time by writing a let function here and not actually defining any variables. Okay, which is fine. So, again, here's our let. So the first part of the let is the word let. Second part is the variable environment, just like we've defined up to this point, right? What's the third part? Hopefully this will be an aha moment for some people. Somebody usually doesn't answer. Then we'll let people who usually answer. All right, I'll take anybody. Huh? This guy right here. That's the you're saying a function? Okay, that's what that specific one is there. I want the generic pieces of a let. So I agree. In this particular case, we are calling a function. But if you had to generically describe that third part, first part is the word let, second part is a variable environment, the third part is the what? I don't mind the word body. It's the body of the let. Now, I'm looking for, in this case, kind of a synonym for that. What could we call that body in programming terms? Something that a word that we throw around a lot, but maybe don't have a great definition of. What about scope? When I say variable scope, what does that mean to you? If I gave you a quiz and asked you to tell me what is the scope of a variable, what would you say?
Where it can be viewed.
Where it can be used. Okay? The scope of a variable is the environment in which the variable can be used. Would you agree that the scope of this environment, that variable environment, is everything inside there? That is everything that came after part 2, but before the end of the let? The let creates a scope. It creates a scope that is bound by this variable environment. Does that make sense? As the most local environment. This scope, actually, in this case, exists within another scope. So in this case, we have a global scope. Well, we have a local scope to the blah function that has a single variable in it called c. That gets bound when we actually call blah. Then we have a more local scope that gets created in this let expression. So something that's more local than the c is a and b. And then we have the local environment, this local scope. These guys are directly bound by these guys, but also live within the greater scope, which is this. Does that kind of make sense? So if I put something outside of this let, it would not be bound by this environment. Instead, it's only living inside of this environment. Does that make sense? So this is scoping rules. So a let has 3 parts. It has the word let, it has the variable environment, so an environment, and lastly, it has the scope. And I'm okay with the word body. Your book would probably use the word body. The reason I chose to harp on the word scope is to kind of start connecting some dots for us. So it would be the body of the let expression. See, this makes it look like there's a zillion lines of code by doing this. Let's see. So if we're looking at a let, we're going to say this is a var def expression. We'll keep it at that. And what are we going to do? We're going to create a list that has 2 parts. First part is the environment. So if the guy looks, whoa, hello. If the guy looks like this, all right, so this is our let expression we're looking at here. The car is the word let. What's this guy? He's the car of the cooter, right? The car of the cooter is our environment. So our Basel code representation of a var def expression is going to have the first element will be var def expression. Then it's going to contain a list where the first element of the list is the car of the cooter of expr, which will be my environment. And then the second thing will be the car of the cooter, which will be the body, the scope. That make sense? Okay, so we just modified our language where a var def expression, now notice, like, well, we didn't really change that much code here. Before, we had this guy being an equal sign, and we had 2 pieces of information, a variable name and a value. Now, what do we have? We have a scope, I'm sorry, we have a variable environment and a scope that that environment governs. Now we have something we can apply. Now we have something we can use. Okay, so that's how we actually write the Simon syntax for this guy. That's for parse. Parse Simon. Okay, so if we're going to do this in our Simon code, we might create a lambda A, and then have this lambda A. I'm just going to actually steal this code here. Heck, I'm just going to steal this code here. It's shocking how close to Simon scheme is. Okay, so SE4, this Simon code, is going to be a lambda that takes a single parameter and whose body, the body of that lambda, is a let expression, where the let expression defines a variable environment and the stuff we're going to do with it. So actually, let's say plus AC, just so we can test it later on. That make sense? So if we were to call parse on that, get rid of all this extra crap. So we're going to call parse Simon SE4 and then run this. We get a lambda expression whose body, we get a lambda expression that has a list. The first element of the list is the parameter list for that lambda expression, and whose second element is the body of that lambda expression. The body of that lambda expression is a list containing a var_def expression, where the var_def expression contains a list whose first element is a variable environment, and whose second element is the body, or scope. That make sense? So that's parse Simon. All parse Simon does is it turns high-level Simon syntax into high-level Bazel syntax. This is a very strange way of writing a programming language. We use Scheme to implement a language called Simon, which is actually a subset of Scheme. Right? So Simon is a subset of Scheme that is a dumbed-down version of Scheme. Then rather than using Scheme to interpret Simon, we instead turn Simon into something that's not Scheme. That is what we've called Bazel code. Why are we doing that? Why do you think we're doing it that way? Why did I use Scheme to define a brand new language called Simon that looks a lot like Scheme except it doesn't have anywhere near as many features? But then rather than use Scheme to interpret Simon code, which could work, I wrote a parser that converts Simon code into Bazel code, which Bazel code looks like this. Why did I do that?
Data abstraction, kind of like how you have JSON. It's kind of like JavaScript, but it's not. It's trying to encapsulate the gist of the data.
Okay, what I'm doing is data abstraction, but why am I doing it? Isn't this functional Scheme code? That's Scheme code. Oh, excuse me, that's Simon code. No, it's Scheme code. It's the same thing, right? Why am I data abstracting it? Why am I turning it into this other language?
In case you wanted to use it someplace else, maybe you wanted to parse it back into some other language.
Well, okay, the short answer is no. I mean, I guess I could want to do that, make it transportable or something, but is this guy down here really any more transportable than this? Is that guy really more transportable than this? One might argue that's actually cleaner. This is a programming language theory class. We already have an interpreter sitting in front of us. It's called Dr. Racket. It knows how to interpret scheme language, which would mean it also knows how to interpret Simon, because Simon is made in the image of scheme. Counts. Okay. So why did I convert it into Bazel? So that we would have the experience of writing our own interpreter to interpret Bazel code, rather than relying on the interpreter that's already written to interpret scheme code, which is functionally identical to Simon code. Does that make sense? So it's to create more work for us so that we can learn about writing interpreters. Why use a wheel when you can reinvent it? That's what the old saying is, right?
So you invented the wheels in the car?
What's up?
Since you invented the wheels in your car,
No, wheels of my car already exist.
why didn't you reinvent them?
I'm doing it right now. But then I appreciated the fact that the wheels were already made. So I went back to regular wheels. All right, so does this make sense? We're actually going to write an interpreter that knows how to interpret Bazel code, which looks different than scheme code. So we're, in essence, writing Dr. Racket for Bazel
In Dr. Rack.
in Dr. Racket. Okay, so getting back to what we were doing before. A little space in here. We were writing apply expression. Apply expression takes in Bazel code. Actually, do we have a that's process scope, head scope. Okay, that's fine. So apply expression does what? It takes in compiled code, that is Simon, the parsed version of Simon, which is a shift, a translation into Bazel. So it takes in Bazel code as well as an environment, and it processes that. So what does it do? If it sees a lit expression, it just boils down to that value. Because a lit expression involves no variables. A lit expression is like this. If I see a 5, it's a 5. Okay? Because what are we trying to do here? We're trying to execute our Bazel code. Otherwise, if I'm looking at a var expression, what's a var expression? A var expression looks like this. That means we have a variable. What do we want to do? We want to resolve that variable. Here's the variable name, so that would be the A in this case, given our environment. So we wrote a function already called resolve var that takes a variable name and an environment, and what does it do? It goes through and either returns the value of that variable after resolving it, or a false if it runs out of places to look. That make sense? Okay, that's what we do for that. Now, let's revisit our var def expression. If we see a var def expression, that is something that looks like this guy down here. This guy, something that looks like him. What do I need to do? If I see something like that, what would you respond with? How would you execute that code? High level's fine. I don't need the actual programming at this point. What should I do in response to that piece of Bazel code? Skippy? Do you even know what the question was? So what are you doing back there?
Homework for course 490.
Somebody else. Somebody other than you. This is not a hard question.
How to make those variables.
Huh?
and then add them together.
Okay, well, say it again. It wasn't completely done what you said. What's the first thing you said?
Gotta make those two variables.
Okay, stop there. Got to make those two variables. What does it mean to make the variables? You're not wrong. So right now you're on high ground. What does it mean to make those two variables at that point? So I have the screen split here so you can see this is my apply expression so far. Everything you need to answer the question lives right here and lives right here. What does it mean to make those two variables?
You gotta resolve those variables.
No. What does it mean to resolve a variable? I'll let you answer, determine why you are wrong. What does it mean to resolve a variable?
Excellent question.
Brandon?
What does it mean to resolve a variable?
Yep. Man, I really thought he wouldn't even know what I asked.
Almost had them.
Just to like find out what it is.
As, Bill Clinton once said, what does is mean? It depends on your definition of is. What do you mean define what it is? Or get what it is? What do you mean by is in that case? If I have a variable a and I want to resolve a, what am I trying to do?
Find out what it's bound to.
Get its value. Find out what it's bound to. That's all correct. Okay, so resolving a variable says take a variable name and resolve it to its value. That's what variable resolution means. But that's not what I'm doing here, Tina. You said that I want to be creating these variables. I think you said I want to make these variables.
Yes.
Okay, close enough. We'll use that as a synonym for creating.
I'll make a memory address and store that value.
Okay, does that seem like something in your wheelhouse? Something we've done in class already? I promise you the answer to this is something we've already done in class. What's a variable environment?
Scope.
Okay, keep going.
Variables are defined.
Would you,
Access.
here, I'll give you a simple multiple choice. True or false? A variable environment is a collection of scopes. That sounds like a true statement. Okay, so what's a variable environment? It's a list containing 0 or more scopes, where each scope is a collection of variables. Where a variable is a to list, where the first element of it is the name of the variable, the second element of it is its value. Does that make sense? So, Tina has suggested that we make these variables. Right here, let me just highlight this. What does that guy right there look like to you, Tina?
Looks like a list containing one or more two lists.
Okay, and what would you call something like that?
I'd call that a variable environment.
Variable environment or an individual scope. It's fair enough. So that's a variable environment. So I have a variable environment here. Now inside of apply expression, do I have another variable environment? I got one that got passed in, right? So when I called apply expression, either initially or somewhere in the cycle, and I keep calling it recursively on other expressions, I have a current variable environment, the one that I'm currently living in, the one I'm currently governed by. Okay, I might be in some local environment of a local environment of a local environment, in which case I would be living inside of an environment that has 3 scopes, where the most local scope is the one that I'm in, and then there's one outside of that and one outside of that. But the point is, I already have an environment. When I get here, when I'm trying to apply the expression, var-def expression, when you say I need to make those variables, what does it mean to make those variables? If I already have an environment up here called env, and I have a new scope down here that has those 2 variables defined, what does it mean to make that environment?
Take those variables in the current environment.
Build a new environment. Take the current environment and add another scope to it, right? Just so happens, we had written a function called add scope. What does add scope do? Well, it takes in a new scope, and it takes in an environment, and it puts them together. Perfect. Perfect. So it's exactly what we need. All right, so what do I want to do? Well, if I'm here and I'm looking at a var def expression, I need to, well, one of the things I'm going to need to do is, in fact, expand my environment. And we'll do that in a moment. Now, getting back down to this thing, what's the second element here? So there's my variable environment. What's this guy? And here, just so we can make it something that our language can currently process, let me write it this way. Let me just close this guy off. Oh, hello. Don't write any of that down. All right. So here's my var def expression. First guy here is my variable environment, my new scope, the one I need to extend my current environment with. What's this guy? It actually didn't get parsed right. Hold on, 1 second. Everybody relax. Oh, it's because we wrote our parser wrong. I was testing everybody. Parse Simon does what? Creates a list, var def expression. Its parameters are a list with our new environment, as well as what? We need to call parse Simon on this second, on the body. Because that guy should actually be a var expression, not just a. So what we did is we just tacked on the a there. That doesn't exist in Bazel code. An a should actually be a var expression whose one element is an a. So if we run this now, it'll look better. That make sense? So now it probably won't be, but it should be easier to answer the question. If I need to add this variable environment to my, well, actually this guy. If I'm going to add that scope to my current environment, what am I going to do with this guy? What is that guy? Is he a Bazel expression? Yeah, he's a var expression. He is a Bazel expression. He's a legal expression in Bazel language. What do I do with Bazel expressions? I apply them. I got to call apply expression, pass it my Bazel expression, and pass it the environment he should be executed in. Does that make sense? So what am I going to do here if I see a var def expression? I'm going to call apply expression, passing it the Bazel code that I need to run, which is the body of this guy. I need this part. How do I get that part? Well, the car of this guy is that. The catter of this guy is that. Right? Because the cooter of this guy is a list containing a list. So the catter is that list right there. How do I get this guy? I could use the list ref thing, right? Okay, so I'm going to apply expression. Apply expression takes two parameters. One is a Bazel expression, and the other one is an environment. The Bazel expression, I'm going to start off with, I'm going to get the catter of Bazel. That's going to give me that list containing two lists. Well, the list containing two elements. The first element is the list, that's my new variable scope. The second element is my body. So cat or Basil's that, and I want to get list ref. And is it the list followed by the position? That? Or is it the position followed by the list? List ref, yeah. List followed by position. So I did it right. So this will get me bucket 1 of this guy. So what I'm looking at right there is this. So bucket 1, this is bucket 0, this is bucket 1. That'll get me the body, okay, which is a Basil expression. So list ref of the catter should get me exactly what I have highlighted there, which is a Basil expression. So I'm going to call apply expression on that Basil expression along with, I got to pass it an environment. What environment am I going to pass it? I'm going to pass it the same environment I already have, but I need to extend that environment with my new scope. So I'm going to call add scope, passing it my new scope and passing it the current environment. And this guy will boil down to a new environment. Add scope. I need my new scope, which will be the list ref catter Basil 0. Along with my current environment, env. So I'm going to call apply expression, passing it the expression that I'm executing, which is bucket 1 from the catter, along with my brand new environment. The brand new environment is the environment created by adding this scope, the scope defined in that let, var def expression, sorry, along with the existing environment. That make sense? And I'll just throw an else in here just for completeness right now. And let's test this on a let. So I'm just going to take this let expression here. And we'll call that SE7. Okay, so SE7 is going to be a let Simon expression, so Simon language. It's going to be a let expression in Simon language. Passing it, there's my new environment, and there's the actual expression. So what am I going to do? I'm going to parse that, and I'm going to take the parsed version of that. I'm going to call apply expression. Is that what I called it? EXPR? Yep. Passing it my Basil code. That's what parse Simon does, right? Parse Simon gives me Basil code, as well as the empty environment. If you need a reminder, empty environment is a constructor we wrote up here that literally just boils down to the empty list. That is the environment containing 0 scopes. That make sense? So, what should the output of this be? Here's my Simon code. We'll let Simon answer the question. So here's my original Simon code right there. When I parse it, it's going to turn into something that looks like this, which is Basil code. Then I'm calling apply expression, passing it that Basel code as well as the empty environment. What should the output of this Simon code be? So forget about all the parsing and unparsing, just look at your Simon syntax. If you were writing Java, what would the output of this be? If you were writing Simon, what would the output of this be?
If I'm running,
What I have highlighted there is Simon code.
Yeah.
Tell me what that Simon code should do. I'm not even asking you to program. I'm just asking you to tell me what the output of that should be.
I should assign A5, B7, and then another 5.
Well, what? This is the body. This is the scope. This is the body. What's A equal to?
5.
5. So this should boil down to 5.
Yeah.
That makes sense? So I'm writing a program that defines an environment here with two variables in it. A is 5, B is 7, and then executes that. Should give me a 5. Why didn't it give me a 5? Well, let's look at our parse Simon. If the car is a var def expression, and that's what we did up here, right? Var def expression. So that's the false it gave us, but I'm actually surprised it got in there. We should have gotten a 5 from this, at least in my mind. So let's see where we went wrong. So let me quickly output this, just so we have that to work off of. Okay. So this is what we're sending into our, oh, hold on. Why do I have a lambda there? Oh, no wonder. I was always testing you there, Simon. I should be passing it SE7, which should give us a 5. There we go. You failed. Why didn't it work for the lambda? Because we haven't really written that feature into the apply expression yet. Doesn't know how to deal with anything beyond lit expressions, var expressions, and var def expressions. That's the limit of what our Basel interpreter can do at this point. That make sense? Okay, so now we've added to our language the ability to create local environments. Pretty cool. Now, could we do this? Actually, this will be interesting. What should the output of that Simon code be? Keeping in mind what we've accomplished so far today. We added a pretty powerful feature to our language. What does this do? I have two lets, right? So I'm originally passing in the empty environment. I'm adding to that empty environment a new scope, that is this scope. Then I'm adding, and then calling apply expression on the rest of this guy. Then I'm adding another environment, which is this scope. I have two scopes. I have a most local scope, I have a less local scope, and then I have the most global scope, which is nothing. So what's the output of this going to be? Ultimately, that's what's going to output, right? B. B is a variable, right? It's a var expression. Variables boil down to their what? Most local definition. Most local definition of B is what? Is it in this scope? No. Now remember, we are calling resolve variable on that var expression. that's ultimately going to process scope. And it's going to keep peeling scopes off until it finally finds it. So it's not going to find it there, so it's going to peel that scope off and go to this scope. And it will find it in there. So this should boil down to a 7. I mean, we just wrote some pretty powerful code off something pretty simple. We have nested environments we just created with our let expression. This makes sense? Okay. Let's see. What do I want to have you guys do for homework? Oh, that would be a good one. I'll give you all this code as a starting point. All right. And what we're going to do, oh man, I tell you what, this assignment is just evil. Actually, it should not be bad, but it should be very interesting. We are going to add a feature to our language, adding another feature, very similar to what we did today in adding that let expression. We're going to add another feature called a math expression. Okay, so this is for 470. Actually, I'm going to make it even easier for you. We're just going to add something called an add expression. We're only going to support the plus sign, adding numbers. Okay? So let me get to 470. Okay, this is 13. Oh, this could be a very interesting assignment. Okay. Homework number 13. Add an add expression to the Simon language. This means you will need to update parse Simon and apply expression in the code below. You will very likely want to define one or more helper functions as well. An add expression in Simon looks like plus A5. Well, you can say plus 7.5 as well. You know, this is a Simon expression, this is a Simon expression. So it's plus expression, expression. Okay? For example, plus 5, 4 would boil down to 9. Test this using an add expression in the body of a let expression. Make sense what I'm asking you to do? So ultimately, what do I want to happen? Just so you have a clear way to test this. I want this. For example, would boil down to A resolves to 5, C resolves to 7. That would boil down to 12. Summing them. That make sense? I'll divide the code. All right, questions, comments, concerns, bribes. And that is due on Thursday.